Let's move on to talk about strain energy. So strain energy is similar to the elastic potential energy that we have learned in chapter 4 when we talk about work energy power. So I'm going to start by recalling something that we have learned from chapter 4, work energy and power. So from work energy and power, we have already learned that the area under the force displacement graph is equivalent to the work done. Okay, so you can review back the video from chapter 4 in which we learned about graph. If you have force as your y-axis and your x-axis you have your displacement, the area under the graph for that graph will represent the work done. Okay, and we know that if the work done is done by a conservative force, such as work done by gravity or work done by the restoring force of the spring, that work done itself will be equivalent to the gain or loss of potential energy. Or in other words, I believe maybe you can recall the equation. The work done by non-conservative force is equal to the negative change of potential energy. Okay, this is what you may recall from chapter 4. You can review back the relevant videos. Okay, so in this chapter, this potential energy that I mentioned just now we are going to call it a strain energy. Okay, as I said earlier, this strain energy here is similar to the elastic potential energy that we have learned earlier. So this is a force elongation graph. Even though it's force elongation graph, you can think of the elongation as similar to displacement, right? Because technically your object, when it's being pulled or when it's being stretched, that's the amount of stretch or that's the amount of compression that's being experienced by the object. So we can say that the area under the graph over here, we are going to call it as the work done by your hand pulling it, and that work done itself is equivalent to the change of potential energy, and we are going to call that potential energy as strain energy. So this work done, this area over here, we are going to call it as strain energy. Okay, so in our syllabus, if we restrict our analysis to anything that happens below the proportionality limit, so this is the proportionality limit. If you restrict yourself to look at area below the proportionality limit, then basically the area is just a triangle. So if it's a triangle, then now this area can be easily determined. So we know that there's a starting proportional limit, elastic limit, then your offset U point, you have your ultimate tensile strength and fracture. But what happened is everything that happens beyond point A here, it's no longer linear. Anything that happens beyond point A, they are not directly proportional. The force and the elongation are not directly proportional. So this area here are actually very hard to be determined because it's an irregular shape. But from the region from O to A, it's because it's linear, this area here is just a very simple right angle triangle. So if we restrict our study to study of object being stretched within the proportionality limit, then the area is just a simple right angle triangle that can be easily calculated using half the height multiplied by the width of the triangle. So because this triangle is very easy to determine, we know that it's just half multiplied by the y-axis, which is the force, multiplied by the x-axis, which is the elongation. So this area under the graph, which represents strain energy, can now be easily determined. So if your object is not stretched beyond the proportional limit, if the amount of stress that is being applied is within the proportional limit, then the strain energy can be easily calculated using this equation over here. But again, I'd like to warn everyone that this equation is no longer valid once we enter plastic deformation, or once we go beyond the proportional limit, then this equation can no longer be applied. Again, the requirement is to stay below the proportional limit to not have any non-linear component in our stretch, in our stress, in our strain. Okay, so that's strain energy, and that's it for this video.